Okay, last week I have taught you design of continuous beam by using the analysis by using the coefficient in BS 8110, yeah, with the condition that the span of the length almost same and also the QK less than GK. Today we will use another method for the analysis, that is elastic method. Yeah? Okay, before that, before we go further, okay, someone want to join in, Nur Suhana. Okay, we must consider several cases of load combinations. This is because we want to get the maximum impact from the actions. Okay, so we have two load set. We call it load set. The first set is according to the EN Eurocode 1992. That is, we assume that we have several cases. For the load set 1, it is under the European code. The first is alternate span carrying the design variable and permanent load. Yeah? This is called a combination of the variable and permanent load, maximum 1.35 QK plus 1.5 GK, and other span carrying the only design permanent loads, that is 1.35 GK. As you can see here, although it's only design permanent loads, we still have the safety factor here, 1.35. While the other cases is that any two adjacent span carrying the design variable and permanent load, and all other spans carrying only the design permanent loads. So this is what the Eurocode suggested. That is, the first one, alternate span loaded. Yeah, if we have a span on continuous beam like this, let's say we have 4 span. The case 1, yeah, from the alternate span loaded, alternate means maximum. We apply the maximum load, and then the other span minimum, and maximum, then minimum. It is called alternate span loaded. And then for the case 2, we repeat the same like case 1, but this one start with the minimum load 1.35 GK. And then maximum load, minimum and maximum. So this is alternate span loaded. The other one is that adjacent span loaded. We have a friend, Izzatu Izwa, joining in. Okay, the adjacent span loaded, we have 3 cases as well. The adjacent span, that means span 1, span 2, we applied with the maximum load, and then the other 2 is minimum load. Okay, and then minimum, both span here maximum and minimum. Okay, so this is recommended by the Eurocode. Yeah. Okay, the other method is that this is according to the previous code, that is, we call it as UK National Annex. This is called load set 2. If you don't want to, so in Eurocode, they only recommended for load set 1, but we can use other code load arrangement, such as from the UK National Annex here. We call it here as load set 2. Here we have 2 arrangement, all span carrying the design variable and permanent loads. Last time we call it as maximum, and alternate span maximum and minimum. We call it 1.35 GK is a minimum. Okay, looks how the arrangement look like. So according to the load set 2, we only have 3 cases. Yeah, although you got a lot of span here, we got only case 1. That means we applied maximum load for all span. This is called case 1. And for the alternate span, we have case 2 and case 3. Yeah, this is alternate span, maximum, minimum, maximum, minimum. If you got other span, then keep repeating, alternate. And then case 3, we begin with the minimum load, maximum, minimum, and maximum. Okay, we have Valentine join in. Okay, so it's up to us as a designer whether we want to use load set 1 and load set 2. If you can compare the load set 1 and load set 2, it is actually produce similar result. Yeah? Although we see that the load arrangement is quite different. Yeah, this one we considered in the UK, but this one, but either load set 1 or load set 2, it will produce similar answer. So for the designer, we prefer load set 2. Okay, so another thing is that here you will come across with the moment distribution. Moment distribution is the transfer of moment to the less stressed section. This is we have advantage actually. It is reduce the usage of steel at the support. Yeah, we can see later. Okay. There are several conditions for the moment redistribution. That is, the first one, we must assume that the load and the beam remains in equilibrium. Okay, Amelina join in. Sorry. Okay, and then we assume that the continuous beam are dominantly subjected to flexure. And the last one, adjacent span to be in the range of 0.5 to 2. Yeah, so the difference between the adjacent span is 0.5 to 2. Then we can apply for the redistribution. Yeah. So the impact of redistribution, as you can see in the design formula. Yeah. So far we only use K balance is equal 0.16. That is, we assume we don't do redistribution. That means delta here is equal 1.0. Delta is the moment at the section after redistribution divided moment at section before redistribution. And this delta we can calculate K balance. We will input the delta that we use in the design. So last time we don't do redistribution, so it is 1. So you calculate, you get 0.167. So for this coming design, for this example, for today's design, we will use delta here. Yeah. This is called ratio of moment redistribution divided moment before redistribution. Okay. Last week we have example. Yeah, in example 6.2, we use the coefficient in the S8110. Yeah, so we got moment, something like that, and also the shear. But today we will use the same example. Yeah, but we use the elastic analysis. What is elastic analysis? Elastic analysis is just like moment distribution, moment deflection, yeah, that you have already learned in structural analysis. So let's say now we use load combination 2. Yeah, load combination 2 consists of 3, case 1, case 2, and case 3. Yeah, for those who just joined, yeah. So we have 2 load combination, load set 1. Yeah. If you use load set 1, that means you have 5 cases. This one. Okay, Nurul Aina join in. But if you use load set 2, we only have 3 cases. Therefore, now in our example, we use load set 2, which we have 3 cases. Case 1 is maximum, all spent. Case 2, maximum, minimum, maximum. And case 3 begin with the minimum, maximum, and minimum. Yeah, so this is our cases. All right. So this is how we obtain the moment. Yeah. Here we use moment distribution. Yeah. So I think we will look how we do the moment distribution later. What I want to show you here is the how we get the moment. Yeah. Okay. From the moment distribution for case 1, that is maximum for all spent. Yeah. So we have from the moment distribution, we only have moment at the support, yeah, 315.8, 3.1.8. Yeah? Yeah. So this is the result that you got. We got from the analysis. Okay. We need to find what is the moment at the span, right? Yeah. Here. Okay. So for in order to get this moment, we need to calculate what is the shear force, shear force diagram. Therefore, in order to get the shear force diagram, we need to use the free body diagram analysis here. Yeah, you separate AB like this. Yeah, the first span AB, we got the moment, hogging moment, positive 215, while for the BC, we have a anti-clockwise, and on the right side is the clockwise, and so on for the span CD. From when we do like this, yeah, we will get the VA and also VB. Then we have the shear force. Yeah. Example here, we can see that for the first span, okay, we have to use 2 here, principal, moment equilibrium, and force equilibrium. Yeah, for the moment in equilibrium, let's say at B here, B, yeah, moment clockwise at B is equal to 0. Total moment at B here is equal to 0. So we got 215.8 this moment positive, yeah, plus VAB times L. L is 8. Minus, yeah, because this one is anti-clockwise, so minus 3.67. So you got 0, equate with the 0. So we got VAB 107. And then from VAB here, we applied the principle of force in equilibrium. That means total of vertical forces is equal to 0, which is VAB plus VBA, yeah, minus with the load downward, so we equate with the 0, so we got VBA 161.66, yeah, and we repeat at the span BC, yeah, at span BC we got VCB and also VBA, yeah. So I think you already understand how to get this, yeah, from the theory of structures. Yeah. Okay. Then, all right. So we got here our shear force diagram. Yeah. From the shear force diagram, we will get the moment here. Moment at AB. So it's the area in this section. Yeah. You got the area here. We will get moment here. Area at this section, we will get moment at here. And area here, we got moment here. Okay, before we calculate the area, so the first thing first is that you need to get the distance, yeah, the area for the triangle, yeah. So we need x1. So x1 is equal the shear force here divided by the W, yeah. So we got 3.2 meter here. X2 4.8 meter. X3 we got 4 meter. Therefore, the area is 172.32, and area 3 here is 53.6. All right, then we can get the value that we want here. Okay, so that is the moment diagram. Yeah, this is called elastic method, yeah? Elastic method. Okay, all right. Okay, after we got the value here, so how we do the redistribution? Yeah. Look at the moment at the support. Yeah, moment at the support. This one, moment at the support. The blue, the value in blue at the support. In design, we can reduce moment at the support, yeah, up to 30%. The maximum is 30%. Okay. We can reduce moment at support up to 30% from the original value. Here we got 215.8, meaning that it's up to us, yeah, whether to have the maximum or either 10%, 20%, 15%, and so on. Yeah? But the important thing is that look at the moment at the AB. Yeah? Sorry. Which is it? The important thing is that look at the moment at the span here. The original is 172.3. That is from the analysis that we have done here. We got 172.3. Okay, in design, if we just use the moment, the original moment, remember when our beam is at ultimate limit state, this one will will yield first. Yeah? It will reach at ultimate limit state beforehand this value. Yeah, meaning that have you heard about the plastic hinge? Yeah, plastic hinge will occur here, while here is not yet. Yeah, so therefore in design we hope that both of them will reach plastic limit, and the hinge will form about the same time. Yeah. Yeah. Here we will get plastic hinge here and also here. So at ultimate limit state, okay, at ultimate load, hinge will occur. Yeah. Therefore, we hope that both at the support and at the span will reach ultimate limit state with the hinge form here at about the same time. Therefore, for design, we are allowed to modify the moment at the support, yeah, so that during ultimate limit state, hinge will form at both sides. Yeah. Okay. Now look at the value here: 215.8 and 172. So we must bring down this value about the same with 172. It is not necessarily the same value, but about the same, more or less, something like that. So therefore, let's say if we reduce as much as 20%, we will get 172.6. Yeah, it's about the same. Yeah, 172 moment at AB and moment at the support we will reduce to 172.6. But we must remember, when we reduce moment at the support, we need to calculate back here the moment at the span. Yeah, because as you can remember, according to the condition given by the Eurocode, okay, we must assume that distribution remains in equilibrium with the load. Okay, yeah, this one we must maintain the equilibrium of the load. Yeah, therefore, when we reduce here as much as 20%, at span AB, yeah, it's not necessarily here also will increase as much as 20%. Yeah. So therefore, we need to analyze again, yeah, this beam. Yeah. Okay. Now we reduce it as 20%. Yeah, within the allowable value, 30%, the maximum one. So we don't know what is the impact on MAB, MBC, and MCD. Yeah? In this example, we reduce both B and C with the same value. Yeah? Okay. Now in other words, we need to force moment at support B and support C to have a value 172.64. Yeah? Therefore, with the same load, the same action, just now for the case 1, here I just show you one example by using case 1. Yeah, this is case 1. Case 1. This is case 1. Yeah. Actually, we need to analyze for all cases, but here I only show you for the case 1. Okay. Okay, for the case 1, now we have the maximum load. We force the support to have 172.64. Yeah. Then we need to recalculate back what is the VAB, VBA, VBC, VCB, VCD, and VDC. Yeah. Do again with the similar procedure as above. Yeah. Here we got VAB, VBA by using the two principle here, that is moment at B equal to 0. So we have the new shear force 113.1 while VBA we got the new VBA 156.26. And then continue with the spend BC. Yeah, we got the new VCB and VBA. Sorry, this is VBC. Yeah. This is VBC, VCB. And this is VCB. VCB. CB. Okay. After that, after we complete all the calculation of the new shear force, then we plot it again and then determine what is the new x1 and x3 here. This value. Actually, we want to find what is the new moment. Yeah. Therefore, we need to calculate x1 and x3. Yeah, we're using the same like just now. So we got x1 3.36, x3 4 meter, a1 we got 190 kilonewton meter, a3 we have the new one 96.76 kilonewton meter. Yeah, this is the shear force after we do redistribution. Yeah, okay. Now we can see here our diagram, yeah, for the case 1 here. This case 1. The blue color shows the before distribution, yeah, and the red color is after redistribution. Yeah. So now we need to calculate what is the delta B. Yeah, delta B is equal, delta is the redistribution. Moment after redistribution, delta B is here, this is B. This is B. C. Okay, so here is BC. AB, yeah, AB. Where is my cursor? Okay, delta B here, yeah, the reduction of here, yeah. Delta B is equal moment after redistribution 172.64 divided by 215.8, so we got 0.8. Yeah. Delta AB here is equal 160, yeah, after in before. Yeah, we can see that at span AB, span BC and span CD, yeah, this is symmetry, they increase, yeah, due to redistribution at the support. Moment at the span will increase. Therefore, we got the value here greater than 1. Yeah? So according to the design, the value of delta B should be taken as 1. Yeah? If your delta is greater than 1. So we use it as 1. Okay. For the support, we got 0.8. So when we got delta, therefore we can calculate the K balance. Yeah. So the delta B will, determine the new K balance, yeah, here by inserting the delta. For example, if you want to design at the support B, K balance will be 0.363. Yeah, delta here we replace it as 0.8. So you got the new K balance 0.116. Yeah, but for the AB, the K balance remains same as 0.167 because the delta B is greater than 1. So if you replace delta here as 1, so you got 0.167. Okay. Okay, now this diagram shows you moment before and after redistribution. Yeah? So actually in the design we have case 1, case 2 and case 3. Yeah? So meaning that in every cases, yeah, we need to redistribute. Yeah? We need to redistribute. For example, here we have the example. We have 3 cases. So we will distribute, we will redistribute the moment at support B, yeah, for every cases. And then we plot in the same diagram. Yeah. From here, from the diagram, we can draw what we call it as envelope. Yeah. Okay. What is envelope? Yeah. Okay. Let's say now we have analysis. We have calculate moment for the case 1, case 2, case 3. Yeah. So we got like shown in the picture. Yeah. Sorry. Okay, sorry. Okay. What is envelope? Yeah. So this is called envelope. Yeah. Make the bold line at outer moment. Yeah. This is called envelope. Okay. So this is moment before redistribution. Yeah. Okay. So this is called moment envelope. What I am doing here is drawing the envelope of the moment. Yeah, moment envelope. Sorry. Okay, here something like that. That is called moment envelope. Yeah. Okay. Okay, again. We also need to draw the shear envelope. Yeah? This is the shear force, either before or after redistribution. Yeah, for all cases, you need to draw in one drawing, and then we do the envelope. Yeah? My cursor. Sorry. So this is the envelope. We will call it as envelope. Okay, that is the shear envelope. Yeah? So our design must be based on the shear envelope. This is the maximum. For example, if you want to design shear force, so the maximum at the support is 113. For the support B, to the left, 161. and to the right 1, 3, 4, and so on. Yeah. Okay, this figure shows moment after redistribution. Yeah? Remember, we have 3 cases. So all cases, yeah, I will, in this example, we fix the moment 172.6 and calculate for all cases. So we have the new moment after redistribution. Again, we need to draw the envelope. Yeah. So this is the envelope. Okay. Just draw like that. Oh, sorry. Sorry, your friend just joined in. Okay, all right. From this figure, what we can see is that case 1, yeah, case 1, the blue, yeah, this is case 1 after we redistribute. Yeah? We do the distribution, and then we do the same for the case 2. Yeah, for the case 2. The moment, yeah, span AB, it's similar with the case 1, yeah, the result of the moment after we redistribute with the same moment at the support. And for the case 3, the only case 3, the moment is reduced, yeah, yeah. Okay, but the moment that we're gonna use is the maximum. For example, for the span AB, so we use 190, and at the support B, we use 172 in design, while for the BC, we use 96.68. Okay. Okay. Any question?
Doctor.
Last week, the same example. We will use the same example so that you can compare the value of the still you obtain if we do the redistribution. Yeah. So this is the layout plan that we used last week. Yeah. So we need to design this beam. Yeah. This beam. Okay. So we have calculated the action and so on. Yeah. Then for example that we will learn today, we will use the action that we calculated. Okay, now we have a specification. Yeah, we don't want to use the coefficient in the BS. Yeah, actually we can use because here the length is 8 meters for each span. Yeah? But in this example, it is only for the comparison purpose. Yeah? So let's say now we use the load combination 2, yeah, which is when we use load combination 2, when we use load combination 2, we will have this like this. Yeah, this is combination 2. Case 1, maximum for all span, and then maximum, minimum, maximum, and then minimum, maximum, minimum. Yeah. Although you have 10 span, yeah, you only require 3 cases. While if you use the other load set, you require how many cases? You will get 5 cases. So it's tedious, and the result is almost the same. Therefore, we use the load combination set 2. Yeah. Okay. Okay, now our case 1 is maximum all span. Yeah? This one we just discussed just now. I take this example. I have taken this example for our discussion just now. So we have completed for the case 1. Yeah? Okay, now case 2. Case 2, we make maximum, minimum, maximum. Yeah? This is the how we using the moment distribution. Yeah, we need to calculate fixed end moment. Umi want to join? Yeah? Okay, so this is the moment distribution method. Yeah, I bet you know how to calculate it, right? So this is the result that we obtain from the moment distribution. Don't be confused. Moment distribution. Yeah, we got moment at support B 172.7. Yeah, 172.7 because this is symmetrical beam. So then we calculate. Yeah, just now you asked me how to get it. So this is the example, shows you the calculation step by step in your book. Okay, so you have the shear force after this. Yeah, and then case 3. Yeah, this is the case 3. Again, yeah, we need to do moment distribution. Yeah, we got the moment 172.4 at support B and support C. Calculate the shear force, and then we combine all the shear force for each cases in one diagram. Yeah, here, and then draw the envelope. The bold one here is the envelope, the one that I showed you just now. This is called envelope. And this is the envelope. Just draw the envelope like this. Okay. This is called shear envelope. Yeah. Okay, and then calculate what is x1, x2, x3. Yeah. Because why? Because we need to find what is the moment at the span. Yeah, at the span BC and AB. From the moment distribution, we only get the moment at the support. Therefore, by doing like this, so you get the moment. Yeah. So we have the moment here. Okay, so this is our moment. And again, bold it at the outside border. Yeah, it is called moment diagram envelope. Yeah. So now this is the moment from the 3 cases. Yeah, you must draw in one diagram. Yeah. So from this diagram, it's up to you as a designer. Yeah. Whether you want to modify moment at the support or just let it be, then you can design straight away from this diagram. Okay, so let's say you don't want to reduce the moment at the support. It's okay. Yeah, but as I mentioned just now, during the ultimate limit state, moment at span AB will reach the plastic hinge first before the support. Yeah? That is not good in design. Yeah? As you can remember, in design, it is recommended that the failure simultaneously happen at all sections. Yeah? For example, at the support and also at the span. Although here, if you can see here, the moment is much less than this. Yeah. Okay. But okay, if you don't want to do the redistribution, in the case that you don't want to do the redistribution, yeah, since we use elastic method, so we have 3 combination. Case 1, case 2 and case 3. Yeah. So when we want to design for the flexural, for example, we must choose the maximum moment at each point. Yeah. For example, at AB, yeah, this is AB. This is AB, moment AB, and moment at B, okay, and moment BC here, moment BC, and so on. Yeah, this is symmetry. So, for example, if you want to design moment AB, the maximum is 198.9. So we must use the worst moment here, the highest moment experienced by the span AB, which is given by case 3. Yeah, the green one is from the case 3. Case 2. Yeah, case 2 will give you the highest moment. Therefore, when we design, we must use moment 189.9. While at support B, the moment maximum will be given by the case 1. Yeah, case 1. This is from the case 1. While for the BC, it is given by case 3. Yeah, this is case 3. Case 3 here. This is case 1. And this is case 3. This is case 1. So case 1. All right. And this is case 3. Yes. Okay. Okay. Here, we can determine that in conclusion. Yeah. For the analysis by using elastic method, we did 3 combination of load, yeah, according to load combination 2. So we have case 1, case 2, case 3. So each cases will give you maximum moment for the particular point. For example, for case 2 will give maximum moment at span AB. Yeah, for the load combination 2. Yeah, that is maximum, minimum, maximum, and then minimum. For the support B, it will obtain maximum moment from case 1, while for the BC, obtain from the case 3, which is case 3 is minimum, maximum, minimum, maximum. Yeah, right? Any question? Ada soalan? Tak ada soalan. Senyap je. Tak ada soalan Okey.
Ada, doktor.
Apa dia? Tak ada Ada ke tak ada?
Tak ada.
Okey. Dengar ada, doktor. Siapa yang bercakap tadi Tadi. Lady tadi berapa? Siapa?
Saya, doktor.
Dia siapa nama?
Azwa.
Oh, Izzatu Azwa ya? Okay. Okay, now we want to reduce, yeah? Because okay, this is important, yeah? The redistribution. Okay, this is our moment before redistribute. The original moment we have from the 3 cases just now is maximum 215.8. Yeah. Therefore, it's up to you. Yeah? As I mentioned just now in in a PowerPoint, the first presentation, is that we can reduce this value up to 30%, so that the value that we obtained almost similar with the moment at the span. Yeah. So now let's say we reduce, according to the question here given is 20%. Yeah. Okay, 20%. Okay, reduction 20%, meaning that we force every cases to have support moment reduced as 20%. Yeah? Okay, look at here the example. Okay, reduce 20%. So original moment just now is 215.8, and then the reduction is 172. We have discussed earlier in the earlier on. Okay, we have already calculated this one. Case 1. Case 2. Case 2 also, we need to force support B and support C to have value 172. So we have the new one, BA, the shear force. Case 3 also. So we calculate back. This is the shear force. We draw in the same diagram. Yeah, we drew the envelope and then we calculate the X. X here is to determine the area under the shear force, so that you got the moment at the span, as shown here. We got the moment. Once we got the X, so we got the moment, and then we draw in the same diagram for both cases after redistribution, and then we bold it at the outer border. We call it as bending moment envelope. Okay, and also for the shear force. So now for the design, we opt this diagram. We must use this diagram in the design. Yeah? So for design of moment, now we only consider 172 at the support A, support B, and support C, while span AB we got 189. Also, although we have here the smaller value 86.6 given by case 3 after redistribution, but we don't need this value since it is smaller than 189. Yeah, so we design for the biggest value. Also for the span BC, yeah, you can see here there's a negative moment here, yeah, but we need to omit this value. We just use the positive value here, 96.98. Okay, for the shear force, again we need to take value of the maximum shear. For example, support A we have 113, support B we have 156 and 134. Yeah, so those three, only these three value that we use to design the link. Yeah. Okay. So now we design. Yeah. So in your book, there's no solution. Yeah, in your books. Okay. Because the procedure is just keep repeating the example 6.2. Okay, now, but here I show you how to design using the moment after redistribution. Yeah? So this is the plan that we refer just now from the example 6.2. Yeah? Again, we have the data L, B, yeah, the width, the thickness, the beam size. Yeah? This is from the example 6.2. And we also have the nominal cover. We already have, we also have been given, the bar also have been given the value. This is for the tension, so this is for the compression bar, and this is for the link. Okay. Okay. Now we don't need the we need to design the beam A, B, C, D. Yeah. But before that, as usual, we need to calculate what is the effective flange. Right? We have already calculated last week. Yeah. So we have since our beam is continuous beam, so we have moment. We need to design at span AB, BC. Yeah. So span AB will depend, the B width will depend on the L naught. Yeah? L naught here is 0.8 L, while here is 0.7. Therefore, we need to calculate what is the B effective for AB and also BC. Yeah. All right. Then we calculate the action as you have already know last week. Okay, the load, omit here this part. All right. Here, yeah, we got our moment here. Yeah. So actually here we got the analysis, long analysis, yeah, from the previous column. I just take the moment diagram here. Yeah. So our design now, we have 3 moments, yeah. 189 for span AB, support B 172, while BC 96.68. Okay, main reinforcement for AB and CD. For AB we have 189.9. So this is T beam, yeah. Okay, the effective D, effective depth for 54, the moment, and then calculate the moment, because MF, because this is T beam. This is T beam. So what is the difference from that of the previous method is that when you calculate here K, yeah, B we got 0.17. Yeah. 0.017 is less than 0.167. Yeah. Therefore, we design it as just like the rectangular beam. Yeah. This is, and the result here is 4H20. If you remember, example 6.2, we get 5H20, if I'm not mistaken. You can check it here. Yeah. All right. And then we design for support B and C. Yeah. Support B and C. Yeah. The K value here you got. The moment is 173. Why 173? This is because here 172.6. So we round up. We rounded up. 173 here. So you got K 156. But we have we use redistribution 20%. So the value delta is 0.8. As we calculate just now, we got 116. So your K here is greater than K balance here. Therefore, it is the section requires compression steel. Yeah. So calculate D dash X. Yeah. So we have the new value here. 4H20. Yeah. Only 4H. For number of steel. If you compare with the design using the coefficient from BS 8110, we have here 5. Yeah. So now we can see that redistribution reduce the steel number at the support. Yeah. Here. Last time we got 5H and now we only have 4H. So reduce one number of the steel. So BC, again the BC we use the 97. Although we have the two value here, 11.32 and here, but we use the maximum value 96.68. So we got the 2H20. Okay, shear reinforcement. Shear reinforcement also, as I mentioned just now, we need to use the maximum from the redistributed value. Yeah, the support is 113 here. So you do just like last time. The method is similar. Only the value here we have the new one according to the value that we have after redistribution. Yeah, so we have the new value. Okay, again we need to calculate the x1, x2, x3. This one is to locate the position of the vertical shear. Yeah, vertical shear. For example, here H6 200 must be placed at 0.9 meter from the support A. X2 from the support B is 2.17, H6 150, 1.55 meter for H6 200 here. Yeah, here. Okay. So transverse link also need to be calculated. It's in, for the transverse link. Again, the deflection. Yeah, the deflection must use the still at AB. Yeah. So by using the similar procedure, and now this spacing is depend on our arrangement. Now we have here. We just now we arrange in double layer, so we only minus 2 diameter here instead of 3. So we have 2 diameter. So we got 113. Okay, the detailing. Okay, the detailing. Okay, so shows the detailing as just like example 6.2. Yeah. Okay. But you can see here, redistribution has proven to reduce the steel at the support from 5H to 4H only. Okay, any question? Any question? Tak ada soalan?
Doktor,
Ya.
yang redistribution yang reduction untuk moment yang 20% tu dia fix ke ataupun
Tak, itu kalau soalan diberi, kalau you kerja, you kena fikirlah. Maximum 30%. Tapi dia punya regulation is that, okay, this is the one that have not yet redistribute. So kena tengok dekat support ni 2.15 kan, dekat bawah ni 189. Kalau boleh, moment di sini ni hampir lebih kurang aja. Yeah, so that at ultimate limit state, you dah belajar kan, ultimate limit state dia akan fail. So bila sini fail, sini pun sama-sama fail lah, bentuk hinge. Yeah, plastic limit sini pun attain plastic limit. Therefore, we need to reduce this value so that it close to the 189. Yeah? So kita kena reduce lah berapa yang boleh lebih kurang ni. So 20%, let's say 20%, so you got 172. Okay. Tapi when you reduce moment at the support, this one also will be, we don't know whether this will be bigger or less than the value, its original value. It's depend on the analysis actually. But the idea of redistribution is that we want to reduce the moment at the support so that the steel we provided here will be less, because here at the support we also have steel from the column. So in order to avoid congestion, kita tak nak dekat support ni penuh dengan penuh dengan reinforcement. So kalau boleh kita reduce ni so that kuranglah besi-besi dekat dekat beam, ya. Itu adalah satu advantage juga, selain daripada kita nak reduce so that at failure it will create a hinge. Bukan saja hinge kat sini tapi dekat sini juga. Okay, so the maximum that you can reduce is 30%, ya. That is 70% from 215. But if you reduce like 5%, it will give no variation of the number of steel. Yeah? So this is important for example, design for the highly reinforced concrete. For example, if you design for the car park, multiple story car park, kita ada contohnya ada kereta kan, keep on moving sebagainya. For the bridge, let's say, ada lori, ada truck dan sebagainya. So redistribution ni sangat penting lah for the heavily reinforced concrete. Kalau untuk multi-story building, kena tengok juga, ya. Bukan semua yang kita buat lah, tapi sekarang because you nak belajar kan, the purpose. Ya. Okay, ada lagi soalan? Kalau tak ada, saya nak pergi ni pasal you punya project. Ada tak? Ada lagi tak nak tanya?
Doktor.
Ya.
Bila kita akan guna cara ni compare dengan previous punya, doktor?
Okay. Kalau in final exam, let's say the question asks you to do that, so you need to consider. Tapi kalau untuk kerja, you kena tengok lah, macam saya kata tadi, kalau moment ada support tu terlalu tinggi, sometimes the moment ada support much bigger than at the span, so you need to reduce a bit. Itulah dia. Kita nak kurangkan besi dekat ni, kat support. Itu terpulang pada you as a designer. Okay, faham? Okay, ada lagi? Any more question? Kalau tak ada, kita cari attendance dululah.
Doktor.
Ya. Yeah.
Untuk yang area minimum shielding tu, saya tengok tadi dia pakai 33 punya load.
Sekejap ya. Sekarang you nampak apa?
Nampak ni lah, akademik.
Betul, YDM.
Oh, okay. Saya kena pergi. Tadi you tanya apa? Okay, yang mana?
Yang dekat minimum shielding.
Minimum shielding. Minimum shielding.
Dekat gambar tadi yang shielding punya diagram.
Ni ke? Ni.
Ya. Saya tengok tadi dia punya kiraan tu dia pakai yang 33 punya reaction. Kenapa dia tak pakai yang reduction nya?
Ada ke? Minimum.
Bawah sikit tu dia. Tu 33.67.
Ini adalah load. Ni load ni.
Dia assume semua sama 33.67 lah. Sebab tadi yang case 2 tadi ada kurang, ada kurang.
Kejap. Okay. Kalau case 1 maksimum semua kan. Minimum okey. X2. Kalau X3, betul lah. Sebab for the case 1, kejap ni, case 1. Okey, sini kan. Kalau case 3 kan, case 3 tadi kat sini. So dia masih maksimum kan case 3.
Okey.
Okey ya, kita tengok ke sini. X1 ni X1 adalah daripada case 1 kan. 113 ni daripada case 1. So memanglah 33.67. So X2 di sini ni, X2 ni daripada 156 daripada kes berapa? Oh, ini design 156. Okey, kat sini 156. 156 ni pada kes berapa? Saya tak ingat lah. 156 kita tengok dulu. 156. Ini diagram 156. 156 ni daripada kes 2 BBA. Case 2 case 2 pun maksimum juga ni dia nampak ni kan.
Okey.
Lepas tu you tanya lagi satu tadi case satu lagi tadi is tadi design sorry. Ni X3 ni 135. Kita tengok 135 tadi daripada kes mana? 135. Ini baru 135 ingat 135 135 ya 134.7 134 pun sama juga 134.7 dia pun sama maksimum. Ini disebabkan oleh ni. Ya? Sorry. Okey, betul
Faham.
Okey, so macam itulah. Ada lagi. Okay, bagus soalan tu So nanti masa projek tak semestinya projek akan buat macam ni lah kena tengoklah momen. Kalau momen kecil tak payahlah redistribute Okey.
Memang confirm doktor, kita tak boleh masuk ATM sampai jumlah 12.
Memang tak boleh. Kalau ikutkan sekarang ni UTM semester ni memang semua online. Yang sampai bulan 12 tu saya tak sure yang tu. You dapat tahu dari mana tu?
Bangin atau kabar angin, saya pun tak pasti tu.
Tapi yang saya tahu memang di semester semua online. sebab lepas ni pun kita tak boleh lagi berkumpul-kumpul selama 6 bulan kan sekurang-kurangnya kan. Tak boleh bergrup ramai-ramai macam tu lah kan. Macam lecture kan ramai kan. So tak boleh lah. Tapi kalau ikut prediction kan sampai bulan 11 tau COVID-19 ni tak tahulah dia punya tu valid ke tidak. Artificial intelligence prediction daripada China, COVID will disappear end of this year in the world. Tak tahulah betul ke tidak kan. Okay, so kita tengok ni kita tengok projek ada satu grup dah hantar kat saya, dia minta tengok okey.
Doktor, tadi doktor nak cakap apa pasal projek?
Sekejap saya tengok chatting ada apa tadi, ada siapa cakap nampak pula lah. Tak apalah. Okey, saya nak tunjuk okey. Okey. View, rotate. Okay. Now, okay. This is one group, yeah, has given me this, and I promised to correct the layout. So I think it's better for me to discuss with you, so everyone can learn. Okay, kalau tengok kat sini di layout plan is a good try this one. But the problem is that this one you can see here, this is the column, direct one is column I understand this is the column. First that I spot is that we need another column here. Yeah? Why don't you put a column here? Yeah, because remember during the lecture last time, our lecture regarding the size of the beam, we will determine the size of the beam depend on the L over D. So L over D basically L over D basically between 13 to 18 for the beam. Yeah. This is the rule of thumb. Okay, now you see here, you can see here the distance is 4670. So ini kalau this one, the column here to here, so we got the total of this length berapa ni? Berapa tu sorry. 4670 times 3. So you have 14,000. Ini totalnya is 14,000. 14,000. Let's say now we need to, let's say we can assume that L over D 13, 14, 15, 16, 17, 18. Let's say we adopt it as L over D, katakan now let's say we L over D 15, 15. So what is the D? So L is equal berapa situ 15 darab dengan D. So your size of beam is let's say size of beam 600 600, let's say you minus with cover, minus with link 8, katalah 12 diameter. 600 ya, minus with the cover, minus link 30. Sorry. Minus link 8. Minus so your D is 552 So 552 ni when I calculate 600 minus cover minus link diameter minus one layer of steel so we got 552 times 15 berapa tu darab dengan 15 so you have 8 lebih kurang 8,000 8,000 so now look at here ni di total 14,000 so this one cannot be accepted this one is not accepted you must your spend must less than 8,000 maybe you put here kalau if you want to put here column the distance here is more than 8,000 so in other words you need to put column kat mana dekat sinilah sini kena ada column sini pun kena ada column faham tak sini pun sama juga there must be column here. Nak mudahkan lagi ni semua ada kolom. Kalau tak ini akan jadi point load. Okey jugalah. Kalau tak ada ni boleh jadi point load dia. This one also point load. Okay. So this one we must for the here you can put the what is the line on it. You can put beam here. Okay. Ada nak tanya tak? If you don't want to put beam here, it become a big slab, one-way slab, a big one-way slab. This is berapa ni distance ni? 5 and then this one is 14,000 it's so big so that's why we need to put the beam here. Okay, any question? Dah cuba belum? Boleh cakap chat. Data ada yang dah update UTM Smart Internet buat hal katanya. Tak apa. Kita nak tanya sikit yang 800. Okey, yang ni yang 800 apa ni? Doktor nak tanya sikit yang 800. Oh, okey. Nanti saya explain balik. Yang ni faham tak? Okay, faham. Dah faham, okay Okay, so basically lah you punya macam inilah. But maybe if you want boleh juga letak sini kolom. Letak kolom sini boleh juga. But if you don't have column here, it is also good because it become a point load to this beam okay. Okay, ada yang tanya yang tadi okay, this one Excel. Doktor, boleh kami letak beam dekat hall tu kan? Boleh kami tidak letak. Tengok dulu macam saya kata tadi. Ya, because mana tadi ya? If you don't put beam here, yeah, it become a big slab sini ni. I'm afraid that the crack will not pass when you do the cracking, checking for the slab nanti ya. Yeah, because now the slab here is quite big ya. Berapa ni? 5,000 and 14,000. Yeah. So it become a one way. Sekejap berapa tu? 14,000 campur dengan. I'm afraid that you will need a very thick slab. Yeah? So might as well you put the beam here. Itu aja my comment.
Doktor.
Yeah.
Maknanya kita ada satu je kan slab one way.
Ya, yeah, betul.
Untuk stand DC tu kan?
Ya.
Okay. Betul.
So yang ni, this one you can put itu tangga kan. Kalau tangga you boleh crosskan ya, this one. Macam ni. Ni pun tangga crosskan. So you know this one case berapa yeah? Okay, mana faham So this is one way slab. Okay. So must remember, you must draw the drawing draw the beam Nice drawing. Like this example. Ni macam ni Not the just one line like that. Tadi ada orang tanya sekejap saya nak tunjuk. Macam saya erase ini dulu. Okay, ada kawan you tanya about the Okay, kita tengok Okay, ini saya kecilkan sikit. Okay, I will erase this one. Okay, before that saya akan buka ni. Okay. Tengok AI is the distance to allow for tensile force due to shear. Ni Z cot theta batu. If you don't want to calculate this, can conservatively taken as 1.125D. So AI is actually you can assume it as 1.125D. Yeah. So yang ini. So let's say sekarang so your distance saya kata D1 lah. This one is equal 0.3 times kita ada 8,000 kan, 8,000 minus 1.15 D darab D dia berapa D let's say 400 or 454 So you got berapa tu? .3 times 8,000 minus 1.125 times 4.4. So you have 1889 almost lebih kurang 900 lah ya. Okay. So From here, from the center of the beam to the first cut off kat sini ni 1900 ya. So if you cut more, if you cut less, then it is okay lah. Yeah? If you want to cut 900, 800, it's okay. So you can use this value is the maximum value here, but you can cut less than this one. Yeah. So tentang dekat sini ni kenapa? Ya. Sekejap. Kenapa kat sini 800 ya? Sekejap. Ini kita punya calculation tadi kan, 1900. Yang ni 800 ni adalah sebenarnya daripada, kejap saya cari desktop. Okay. Last time lah ya. Sekejap ya. Mana tadi? Okay. Last time this one is 0.1 L ya, yang ini according to the British code ini 0.1 L, while here is 0.15 L. Okay. Okay. Ini BS ya, dulu BS. This is from BS. Simplified code, simplified rules due to BS BS 8110. The value is 0.1 L, 1 L, and here is 0.15 L. But when now we refer to the Eurocode, so the simplified detailing also we need to refer to the new one. Yeah? This is the new one. Okay, but the example here, the distance given in the example. Here is referring to the previous code. Yeah. Therefore, the solution here is got 800. Yeah. Faham tak? Tadi siapa yang tanya? Ini kan? Ni 0.1 L. Ni ikut lama punya Ni ikut lama semua ni. Kalau ikut baru, ya. Tapi it is not wrong because the maximum is what we calculated 900 From here to here mesti potong 1900, but now we only cut at 800, so it is safe. Meaning that if we refer to the previous code, our design still safe. Okay. Tadi siapa tanya? Tongxing ya? Is it Tongxing? Okay. Okay. So Tongxing okay Alright. Any more question? Ada apa-apa lagi? Doktor? Okay. Size beam tu you kira sendiri. Betul. You boleh kira sendiri size beam tu. Kan hari tu saya dah ajar you macam mana determination of size of beam. Yeah, it's depend on the L over H kan equal to 13 to 18. Yeah, so you got the L, so you can estimate the H. Once you get the H, then you can get the B. Yeah, B is equal 0.3 to 0.6 H kan. Okay, clear eh? So this one also 0.15 times 8,000. So you get 1,200 nih. But according to the Eurocode, it must be cut at 1,900. So okay lah, it's less than this one. This is Eurocode. Yeah? Okay, if there's no more question, then we will end up the meeting. Okay, boleh faham tak? Senyap je. Kenapa tak nak cakap? Bisu semua.
Faham, doktor.
Faham, okay. So, sekarang ni you establish dulu you punya plan and then terus buat continuous beam ya. Okay, so seorang mesti buat satu continuous beam. Okay, saya lukis balik sini ya. Terpadam ni. So here continuous beam. This is we got a beam here. Column. Okay, so let's say siapa tadi? Izwa. Izwa, you can design. Sorry. Izwa, let's say you design this beam, one continuous beam, and then one simply spotted beam, okay, and then one panel. This panel is two-way slab, this panel and this one way. Okay, that means each student must do 4 design. Simply spotted beam, one continuous beam, one way slab and two-way slab. Okay, that's it. So in one group you must divide work between your member. If Izatu has already designed this, so Tonsing must choose other, continuous beam. This one maybe, or this one, or this one, and make sure that the load, the action must be for the variable load must be according to its function. This is the hall. So what is the QK? Determined from the BS that I have given to you. This one classroom,
Doktor. And one way slab kan ada satu je kan?
Tak apa, semua orang buat tu pun tak apa.
Oh, so sekiranya macam semua orang buat benda yang untuk one way tu sama je lah.
Boleh. Kan lain, the distance kan lain, between the group lain kan? But everyone must do this lah, because if you don't do, you don't have experience how to design.
Oh, okay doktor.
Ya.
Nak tanya yang QK kan, yang permanent action tu.
Macam mana QK
yang permanent action tu yang kena bagi dia excluding self-weight kan?
Yes.
Then dalam calculation tu kita kena consider self-weight dengan self-weight dia kah?
Dalam projek ke dalam apa?
Project.
Dalam projek ni you kena cari self-weight from the shilling, from the finishers, biasanya dia punya value is 1.5 to 1.0 to 1. Less than 2 1.5. Basically 1.5 lah orang pakai. That is from the shielding and also the tiles, finishes and so on.
Okay. Yang tinggi untuk wall tu doktor kita
3
assume.
meter, 3 meter. Biasalah
3 meter.
satu tingkat kan 3 meter kan.
Oh, okay. Thank you.
Okay, welcome. Miss Everything ni siapa? Miss Everything siapa nama?
Indi dah.
Hah?
Indi.
Indi?
Indi ya.
Oh, Andy. Oh, saya ingat perempuan.
Dia memang perempuan doktor.
Okey. Okey ya. Tak ada lagi soalan?
Doctor,
Ya.
can I, if I put one beam from beam at 7, A until D, one long beam, one long
From
from A to D.
A to D, A to D, A to D. Okay. Okay. Yeah, okay.
Can we assume that as continuous beam?
Yes, of course.
Okay, thank you.
Okay. Yeah, it's depend. Your plan is depend. Your design will depend on your floor plan. Yeah. If just now, what's your name just now?
Ida.
Eda. If you put beam here, yeah, continuous here to here. This is continuous beam. Okay.
Okay.
You can also put here. Okay. Something like that. Boleh juga, no problem.
Okay. Thank you.
Okay. Ada lagi? Any more?
Doktor.
Yeah.
Doktor. Kalau kita letak beam sepanjang span BC tu,
BC, span BC.
mana kita letak beam support
Sini pun ada.
Ah,
Sini ada.
nanti bukan tak ada simply beam ke?
Mana ada simply beam?
Maksudnya
Yalah. Ni
Yeah.
janganlah letak.
mana tak payah letak satu kan?
Ya, boleh. Plan macam ni pun okey juga, boleh je. Okay. So here we have a column lah. Okay. Okay ya. Any more question? Tak ada?
Doktor.
Ya saya.
Saya nak tanya pasal size beam. Yang dekat belakangan tu ada tulis 250 darab 600. Itu pakaian tu ke ataupun kita kena design
Ni macam mana dapat saiz ni? Ke apa maksudnya?
Saya nak tahu kita pakai nilai ni nilai fix ke ataupun kita boleh design?
Nilai ni ya, you boleh assume and then you design lah, ataupun you gunakan L over D tadi boleh dapat juga value.
Oh, okay, faham.
Tapi kalau ini kan, ni simply spotted beam ni biasa kita akan letak, kita round up lah 525 or 550 something like that. It's not normal lah the size here. It's 510. Yeah, so the owner can change this. Whose drawing is this? An Autodesk student version. Produced by, I don't know, got no name, yeah. you boleh assume ataupun gunakan rules L over D how to determine the size of the beam that you learned last time. Okay? Any more question? Tak ada
Doktor,
Yeah.
tadi kan doktor ada tunjuk yang 522 darab dengan 18 kan? Ke 15? Kan? Yang 522 tadi tu value apa tu?
D. Sebab dekat sini this student ni lah the owner of this drawing, dia gunakan 600 kan. This is H. Kan? H. So daripada H boleh dapat D kan. Katalah you punya cover 30, size steel link 8, and then size steel tension 20. So tolak-tolak dapat 522 lah.
Oh. Okay. Lepas tu dia dah dengan 15 tu nak check untuk distance apa column.
Because tadi ni plan ni dia tak ada kolom ni. So it's too long. The maximum we can go is tadi berapa?
8,000
kan? 8,000 je kan. Kalau you tak ada kolom sini pun tak boleh. It's exceed than 8,000 tadi.
Okay, dapat. Yang saya doktor.
Okay, sama. Okay, ada lagi? Okay, I will stop recording.